Oops, let me zoom out a little bit. So here's what I came up with. Does yours look about the same? Okay, good. Let me turn off that light. Your triangle one's different?
Yeah, I forgot about it. Yeah, my triangle. Because I didn't think that was equilateral.
Okay, it is equilateral. At least according to the computer program I used to make it. So,
through the bottom middle, I got only one.
oh, okay. There's actually a lot for that one. But it might be hard to see that without using like a mirror. Had I handed you guys mirrors, you probably would have been able to find more of them. Okay? I just didn't want to hassle with all that today. Okay, but yeah, this is what they should look like. Okay? What I want you to see, here's the pattern I want you to see. How many sides does this first one have?
3.
Yep.
3, yes.
So in this one I would say n is equal to 3, right? Because we use n for the number of sides. How many lines of symmetry does it have?
4.
Has 3 lines, right? Here's 1, 2, 3. That one is equilateral, by the way. All of these are regular, which means all of them are equilateral. So when n equals 3, you have 3 lines of symmetry. Okay? What does n equal here?
4.
4. How many lines of symmetry do you have? 1, 2, 3, 4. So when n equals 4, you have 4 lines of symmetry. Here, n equals 5. How many lines would you guess are there?
Probably 5.
Probably 5. Yeah. Okay. And I could continue that all the way down here. Here, n equals 6. So there are 6 lines of symmetry. Okay, that's lines of symmetry. Here, n equals 7. So there are 7 lines of symmetry. And n equals 8 here. So there are 8 lines of symmetry. Okay?
Wait. Is n? What does n mean?
N is the number of sides.
Side.
Okay? So like this is a 3-sided figure. And as long as it's regular, it'll have 3 lines of symmetry. It'll also have 3 angles. Okay? So 3 sides, 3 angles, 3 lines of symmetry. 4 sides, 4 angles, 4 lines of symmetry. 5 sides, 5 angles, 5 lines of symmetry. Okay, a lot of bang for your buck out of that one number. Lose you somewhere?
Like, for like that one, like in the middle, bottom middle.
This one?
Like, I got 14 lines.
Okay, if you were just counting from here to the center, that would be 14. But watch this. Here is 1 line. So here's 1, 2,
Yeah.
you see it now?
Yeah.
3, 4, 5, 6, 7.
Yep.
So yes, if you're just counting around, you're actually counting each line twice. Okay, so if you're counting the whole line, there would be 7 lines. Okay? Do you see how on all of these, as long as you drew them well, it didn't work so well for me here, but as long as you drew them fairly well, all the lines of symmetry meet in one point. Okay? That one point is called the center of the figure. Okay? So that one point where the lines of symmetry meet is called the center. I think I sort of mentioned that yesterday. And do you remember when we talked about parallelograms having 2-fold rotational symmetry? Like that you could rotate it twice and have it land back on itself? Well, if you were to spin this triangle around this point, how many times could you line up the figure before it came back to the original? 3. Yep. So this would have 3-fold rotational symmetry on top of the lines of symmetry. Has what we call 3-fold rotational symmetry. Because if I took this triangle, I could spin it once, I could spin it again, and then the third time it would land back on itself. Okay, so you could spin, spin, and then the third time it would be back in its original position. How many times could you spin this one? 4. This one has 4-fold rotational symmetry. So if you had to guess, how many times could you spin this one? 5, yeah. So if it's a 5-sided figure, it has 5 lines of symmetry and it has 5-fold rotational symmetry. Okay, which means you could spin it 5 times before it lands back on itself. Do you need me to write all of these in? Good. Okay, this one would have 6-fold rotational symmetry with this being the center. Okay, so that's the point that you're spinning around. This would have 7-fold rotational symmetry. This would have 8-fold rotational symmetry. If I gave you a 16-gon, what kind of rotational symmetry would it have? 16-fold rotational symmetry. Yep. Okay, so pretty simple there, right? Hopefully. What do you notice about the location of the lines of symmetry? Like, let's start with the square. Let's start with this one. Where do the lines go, Rachel?
It's like between bisects every angle and then
Good. So we have lines of symmetry that go from vertex to vertex. Okay, so these ones go vertex to vertex. And then we also have ones that they bisect the sides. So there and there. And those are actually perpendicular bisectors. Okay, but what about this one? Does that same thing happen? What about this one? Hi.
So sorry
That's okay.
to interrupt. I have a quick question. On 7-9,
Uh-huh.
we cut out the inequality
Yes.
because we already did it.
Mm-hmm. Yeah.
So we're only really covering this first side.
Yes.
Okay.
Yeah.
I don't know why I blanked out on that, but
Yeah.
I did. Thank you.
Yep. Okay, so back to this. Does that same thing happen here? Do you have lines? So you have lines that go corner to corner. So these all go corner to corner. And then the other ones go side to side, right? So these ones go from corner to corner. These ones go, I need a new marker. These ones go bisector to bisector. Okay. Does that same thing happen here? Do you go corner to corner here?
No.
No. This line, see how it goes through a vertex here, but then a side here? Does that happen here? Okay, so here we go corner to corner and side to side. Okay, every other, so what do those have in common? They're all even numbers, that's right. So the even number of sides, if n is even, the wrong one again, and I'll write this down for you in a minute. If n is even, your lines of symmetry are all either from vertex to vertex or they're the perpendicular bisectors of the sides. Okay? If it's odd, like this one, and this one, every one of your lines goes through one vertex and then is the perpendicular bisector of the opposite side. Okay? So when it's even, you're going corner to corner or bisector to bisector. When it's odd, you're going corner bisector. So each line kind of does both things, corner bisector. And that's because there's not an even number of vertices, so you wouldn't be able to pair up all of the vertices. Okay? So what I would jot down someplace is when n is even, the lines of symmetry go vertex to vertex and perpendicular bisector of opposite sides. Oh, you can't see what I'm writing. I'm so sorry. Okay. So when n is even, the lines of symmetry go from vertex to vertex, and then they also go the perpendicular bisectors of the opposite sides. When n is odd, I fit that here. I'm gonna sure try. You can write this wherever it fits for you. When n is odd, the lines of symmetry go from vertex and then they are the perpendicular bisector of the opposite side. Okay. Hopefully that makes sense in words, but if that doesn't make sense in words to you, at least if it makes sense to you in the picture, you should be good to go. Okay? But all of this other stuff should be super easy. If I say I have a 12-sided figure, how many lines of symmetry does it have? 12. Okay? It also has 12-fold rotational symmetry. Okay? So that one number kind of tells you everything that you need to know. Does that make sense? Okay. Stop that real quick.